Start recording. There we go. You guys can't see anything. Let's try this again. Okay, good stuff. Okay. Corrosion is the oxidation of any metal. Yep. Rusting, on the other hand, is the oxidation of iron metal specifically. So we're going to consider three metals: iron, zinc, and aluminum. These are all relative, they're all on the bottom half of your chart, yes? They're all on the bottom half of the chart. And if we look at their oxidation potentials, their oxidation potentials are all quite positive. That means that iron, zinc, and aluminum are all relatively strong reducing agents. Which means they are good at getting oxidized. Okay, so they're all good at getting oxidized. And so if we throw them outside, the aluminum ladder, oh, it still looks shiny. The zinc coated watering can, oh, it still looks shiny. But the iron, the steel, which is mostly iron, cement mixer looks rusty. So what is the difference? Why does that one look terrible and the other two look great? The reason is that when aluminum and zinc oxide form, they form smooth, hard oxide layers. Yeah? So it would be like, you know, you got your O, Al, O, Al, O, right? And that little guy just forms a very stable barrier. Okay, smooth, hard oxide layers. Iron is different from aluminum and oxide and zinc in that it does not form a smooth, hard oxide. Instead, it can flake off, exposing fresh iron surface to oxidizing agents. So here we have a tin can, which is, the can is primarily made of steel. And if we coat it with tin, SN, that protects the surface because the tin will oxidize instead of the iron. Yeah, steel, remember, is but it's mostly iron. Okay, we don't care about the rest of it because carbon doesn't really oxidize, not like that anyway. Yeah? Well, then it falls apart. And people have had cars that literally, you know, the bumper falls off because there's nothing left to attach it to because the darn thing rusted through. It's not as common anymore because they have better rust prevention measures, but yes. If like a rusty car, yeah. I mean, it's not likely these days, right? Because you don't get huge patches of rust, but yeah, old cars, especially if you lived somewhere where there was like salt on the roads during the winter a lot, you could have like, you know, a hole in your whatever. I know my dad's old Volkswagen Beetle, there was a hole in the floor. Oh, this is the 1970s. You know, things were different back then. The heating system didn't work too well when you first started out. So sometimes, because my school was on the way to his school, he would drive me to school, and he would reach around the outside because his arms were long, and he'd be scraping the outside because it would fog up again, and I'd be scraping the inside because it would there would be frost forming on the inside and frost forming on the outside, and we'd both be like, I'd be scraping in front of him and he'd be scraping in front of him, and you know, good times, right? All right. And it was one of these ones where you have to roll down the window like this, right? But it was sticky, so you'd have to roll down the window like this. Yeah, super fun. All right, so let's take a look at our chart and compare tin and tin and iron. Where is tin? Tin. It's coated in tin. So what kind of tin is it coated in? Metal. Okay, so it turns out actually that tin is not as good at getting oxidized as iron, but it does form a barrier, okay? And tin oxide provides a nice hard layer, okay? Yes. So if you coated it in aluminum, that would be better, because then the aluminum would, even if you got a scratch in it, the aluminum would oxidize instead. Yes? So if you have a tin can and you get a dent in it, I'll be with you in just a second, Brian. If you have a tin can and you get a dent in it, because Fe oxidizes more readily. You guys okay with the word readily? Yes, good. Than Sn. So Sn provides only physical protection. Against rusting. Against to the what? ST. There we go. It provides a physical barrier. Just like painting, you could paint the can. Yes? Painting the can would also provide a physical barrier. However, if the can is dented or pitted or scratched, the tin coating is broken. Okay, and water can collect in the indentations. So here we have this pitted iron surface, and that's a big drop of water. We are going to actually watch the video at this point because it's kind of nicer with the animations. Okay. Where did it go? There we are. Uh-oh. How, yes?
I'm pretty sure like when I was a record, sort of, made out of a lot of
also because aluminum is light. Okay. Yeah, so aluminum is a fairly light metal as well. Okay. Here we go. Where's our video? What? No. Yeah. My connection to the internet is offline. Okay. Why am I offline?
none of that. Like, I don't care about this.
It does this every day. It's very irritating. Okay. Woo. Okay. We want WCLN. Why is it not typing? Corrosion causes. Oh my God. There we go. Okay, here we go. Woo. Okay. Well, this is not working. Okay, fine. I'm gonna wing it. That's all right. We'll see if I can remember exactly what's here. Okay, so we have here water. Okay, that's a water droplet. And we have iron, obviously, here. Now, what happens is that over here, iron gets oxidized and it turns into Fe2+, which then like floats off into the water. Yes? Now this region over here, oh no, it says that down below. As oxidation occurs, the pit increases in size. Yes, because you're now taking solid iron and turning it into Fe2+. We have a mini galvanic cell here. Okay, oxidation occurs at the pit. So this area is called the anode region of the metal. And so we can fill that in here. This is the anode region. Is the anode always what? Yes. A, O, both vowels, always. All right, now somebody needs to grab onto those electrons. Okay, so the electrons, they move over here. And who's coming along to do that? O2. Okay. So O2 is coming over here. Can you guess what that region is called? That's our cathode region. Okay, so we're going to have, we have O2 plus, and I need to look this one up because it's not actually on our chart, which is a pain in the butt, but that's okay. There we go. All right, 1/2 O2 plus H2O plus 2 electrons goes to 2 OH minus. So it's reduced in the presence of water. And this is now our cathode region. So now in the solution, in the water, we now have iron and we have hydroxide. What happens when iron and hydroxide are in solution together? They will form a precipitate. Okay, so we get reduction that takes place near the point where the water, iron, and air meet. So this area is called the cathode region. Iron is low solubility with hydroxide because it is all others. That includes iron 2+ and iron 3+. So these two guys get together and they form FeOH2 solid. So we get that precipitate formed. And that precipitate builds up on the surface of the iron. Okay, so you'll notice we've got this precipitate happening here. Okay. Thus ends the part of corrosion you should know, understand, and feel comfortable with. What happens next is included for correctness, but it is unlikely you'll need to know the details. You can get further oxidation, and you will get further oxidation from Fe2+ to Fe3+. So it will then form FeOH3, and it's also going to form iron oxide with some waters in it. And I believe that it is the fact that we have this variable number of waters in there that makes the crystal structure of iron 3 oxide irregular, which means that the rust, have you ever flaked rust off of something? It's flaky. Do you guys know that rust is flaky? Have you ever experienced rust anywhere in real life? Yeah? Okay, it's flaky. And I think that's because it doesn't form like a very regular crystal because of that variable amount of water. That's my guess. I don't know that for sure. Okay? There's some exercises on this. We're not going to look at those. You can look at them if you want to. The more important point, because you're going to come across it more often, is corrosion prevention. And again, I would love to show you this little video, but probably the video is not going to work, so we'll just go through it together. So we have our barrier methods. God, it sounds like I'm teaching sex ed here or something, doesn't it? Barrier methods. Well, that's what I hear. I mean, I don't know. Anyway, whatever. So, barrier methods, these are physical methods, yeah? These are physical methods of preventing corrosion. These methods over here are electrochemical methods. Okay, so how can we prevent corrosion? Easy peasy, let's paint it. Yes? Let's oil it or grease it. What does this do? It prevents both the oxygen and the water from touching the iron. And if the water and the oxygen cannot touch the iron, then can't work. So paint it. That's why all our cars are painted. I mean, it makes it look nice, but would it be cheaper not to paint the car? Sure it would, but at that point now you have exposed steel and it will rust. And so this works really well for big pieces like boats, cars, things like that. If you have moving parts, painting it doesn't work so well because you get those parts move against each other and the paint would flake off. So oil or grease, like on a bike chain. That's why you have to continually make sure your bike chain is greased properly so that you don't end up with rust. And we can also electroplate our iron with a different metal. So that would be like, for example, tin. Okay, it prevents the air and the oxygen from touching the iron, but it doesn't actually get preferentially oxidized, so it doesn't help it in a chemical sense. That's why it's a physical method, and it is not an electrochemical method. So it's just a barrier. Okay, now, these electrochemical methods, also known as sacrificial methods, what we do is we add a more reactive metal, and by more reactive metal, we mean a more easily oxidized metal. Okay, so what we've done here is our little aluminum looks like this, okay, and we've stuck it all over the iron. Yes? This is our Fe. This is our Al.
It's just like, see, like, I don't want to because.
No, because it's like, if this is my piece of iron, and this is my piece of aluminum, I just do this. I just have little blocks. This is not a particle level diagram. This is like a literal, here's a big piece of iron with a piece of aluminum stuck to it.
Oh.
Yes? Now, let's assume that here we have aluminum. Who would oxygen rather react with? Who would oxygen rather take electrons from? Who would rather lose electrons? The iron or the aluminum? The aluminum. And guess what? If aluminum is losing electrons, where do those electrons go? They can go into the neighboring iron. Yes? Those electrons go into the neighboring iron. And from there, the oxygen can then pick up the electrons. But if the electrons are moving into the iron, what does that make the iron? The iron is then a... If the electrons move from the aluminum to the iron, that makes our iron a cathode. Can a cathode get oxidized? No, because we're pumping electrons into it. Yes? Now, something else can come along and pick up those electrons. In fact, they have to in order for this process to happen, but yeah. So the more reactive metal will be oxidized instead. Electrons from the oxidation move into the iron and because the electrons move from the aluminum, Fe is the cathode. A cathode cannot be oxidized because it's always got electrons moving into it. So then O2 can get reduced at the cathode region. Okay. And because what we've done by attaching a more reactive metal, a more easily oxidized metal, we have turned iron into the cathode. This method is known as cathodic protection. Is good? Okay. Yes. Is chromium? Yes. Yes, I believe so. Let's just take a quick look at chromium here, just so I don't give you wrong information. Oh, by the way, I taught you guys something wrong yesterday, so I need to correct that today. Yeah, chromium is below iron. That's why back in the past, there used to be a lot of chrome bumpers. They would plate the bumper in chrome before we had like plastic bumpers. And that's because the chrome would oxidize instead, and you'd end up with a layer of chromium oxide protecting the iron. And even if you got a scratch in it, the chrome would still be like, oh, I still would like to give up my electrons, and those electrons would then move into the iron, making the iron the cathode and preventing the iron from oxidizing. Yesterday, what did I teach you that was wrong? It was, oh yeah, it was an electrolytic cell. We were talking about the electrolysis. And we were talking about, it was the question that you asked. Nickel and iron? Was it nickel and iron? Nickel and copper? Oh, it must have been, it was in our notes. Okay, let's see. There we go. Yeah, okay, so this was in yesterday's notes. So, this was wrong yesterday because the oxidation potential of copper is negative 0.34 volts. So it would not be a spontaneous reaction. Yeah, we don't actually want copper to oxidize at all. Copper is the cathode, so it won't be oxidizing anyway. Well, what we're saying though is that the nickel would not spontaneously react with the copper in that cell because the E naught would be negative 0.60. Does that make sense? So I was like going on and on about this. It made all this sense. I asked my other block and they were like not pulling anything out. And then I started looking at it. I'm like, hang on, that's not spontaneous. Because actually, if you look at copper metal and nickel, here's copper metal, here's nickel. That is non-spontaneous. Yeah? So we don't have to worry about that. So just ignore that part where I was like, you got to turn it on before you put it in the solution. And I don't know.
So how does this electrically important?
What?
Like
I can't go back and teach yesterday's lesson.
Like if it doesn't react non-spontaneously, how
Okay, but that's not the reaction we want to happen non-spontaneously. The reaction was we don't want nickel to oxidize the copper. What we wanted is for nickel to be oxidized at the anode and then nickel to be reduced at the cathode. Yeah, so we didn't want copper involved in the electrochemistry at all, other than as being a surface for the nickel to plate onto. Does that make more sense? Okay, cool. Does that seem okay, Cynthia? Yeah, I got confused, but we're all good now, I think. Alrighty. So going back here, there is an example that uses both methods, and that is called galvanizing. Galvanizing. And basically, this is where you provide both the barrier you would electroplate the iron with zinc. So we plate the Fe with zinc. And number one, that provides a barrier. But do you remember what happened when we scratched the tin off the iron? What happened when we scratched the tin off the iron? The iron oxidized. But even if we scratch it, the iron gets exposed. The zinc will react with any oxygen because zinc is preferentially oxidized. Yeah. And the zinc, if the hole is not too big, the zinc oxide will actually fill in the scratch or the hole. It'll like cover up the scratch. Okay. Is good? With the other comments at great stuff. Like I went through there today and I came down the stairs and there's like 50 people in one big pile and there's no way through. I was just like, I played my teacher card and I'm like, excuse me, right? But otherwise you would have to go like around, like the whole size of this classroom, basically. You'd have to be like, oh, okay, I'm going around. It's crazy. But yeah, I played the teacher card. I'm like, excuse me. Everyone was very nice. They moved over for me. It was good, but I was like, wow, this is crazy. All right, the downfall of the barrier methods. If the barrier is broken, rusting occurs. Gosh, this sounds just like sex ed. Well, there was this song back in, do you guys know the song by the B-52s, Love Shack? Have you heard that song? Okay, so there's this line in there and then they go, tin roof, rusted. And people thought that meant that somebody was pregnant, but it doesn't really, they just said it. But anyway, so this is I'm like, tin roof rusted. Okay, anyway. Problem with paint. Paint can get scratched, okay? And the iron will be exposed by the scratch and it will rust. No. Please tell me that one of these is working. Okay, I will plug you in. And you've been in there for a second, so you'll probably be okay for the next 10 minutes or so. So, the iron gets exposed, and so the scratch will rust. Problem with grease is it wears off, right? It's not going to last forever, and the exposed iron can rust. The problem with electroplating, and that's like when we have tin, again, just like painting, You can oxidize it. So if oxygen has a choice of reacting with tin or iron, it's going to react with the iron because iron has a higher oxidation potential. Okay. E0 cell, that gives our iron and tin. It's less positive, so that would be our preferential reaction. The iron and the oxygen compared to the tin and the oxygen. And that means the more positive the E0 cell, the more negative the delta G, because delta G is equal to negative NF E0. Do you need to be able to use that formula? Yes, you do. And look, do they give you that formula? Yes, they do. Well, let's go and look. I think it's Faraday's constant. Yes, yes, it is. What is N? N is the number of moles of electrons. So you would have to find that in the balanced redox equation. And where do they give you this equation? That is one of our delta G equations. We can relate delta G to K. Just take a second. Okay, we can relate delta G to E, which means we can also relate K and E through delta G. Yes? If you know the E, you can find G. If you know G, you can find K. If you know K, you can find delta G. If you know delta G, you can find E. K is the equilibrium constant. It's just whatever K is all the time. But if you look, it tells you what is K, the equilibrium constant. So you don't have to be like, Miss Spence, what is N? Oh my God, it tells me. What is F? Does it give me a number for F? Why, yes, it does. Look at that. Yes? Okay, cool. So actually, if you were given an E and you wanted to find K, you don't even have to go through delta G. You could just make these two things equal to each other. Yes? Does that make sense? Yeah? We're not going to spend a lot of time doing that, but it could show up on the exam. But it's just math, so look for the formula and plug things in and do the math. Okay? All right. But what if we coated in a metal lower? This is our sacrificial method where we plate it coated in zinc. Zinc is being oxidized. It acts as the anode. So here is a little picture of cathodic protection. We have a little scratch. You see we have our zinc here. This is our zinc coating. All right, and below that we have our iron, okay, in gray. And we have our little water droplet. And even though we have a scratch in the zinc layer and it is broken through to the iron, over here, zinc is losing electrons instead of iron. Okay, so we get our zinc losing our electrons, and then those electrons zip on over here. So this little iron here has become the cathode region, right? So the zinc is the anode, the iron is the cathode, and then the oxygen will go there, and you'll actually end up with zinc 2+ will end up with zinc coming over here and becoming zinc oxide or zinc hydroxide, and that will fill in the gap. Okay, galvanization, barrier, and sacrificial. Oh. That's the other thing about cathodic protection, is the other word that we use is the sacrificial anode. And the sacrificial anode is always the metal that is more easily oxidized than iron. Okay, and that's because it gets oxidized and it turns into the anode, and because it is the anode, it turns iron into the cathode. It's just new vocabulary that you need to, be aware of. Cathodic protection, sacrificial anode. Important words. Yay. Okay. Cathodic protection, it's really no different from galvanization, other than the fact that galvanization would be like if I dipped this piece of iron, or if I electroplated this iron in zinc and it was all covered in zinc, that would be galvanization. Cathodic protection is usually where we just stick a piece of zinc on there because it's easier. So we might do this to something like if you've got a boat and it's got a propeller, a metal propeller, it's going to be hard to paint the whole thing successfully. So what you might do is you might just stick a big block of zinc to the side of it, and every so often you'll have to replace the zinc as it oxidizes away. Does that make sense? Okay, cool. All right. Oh, look. The white patches on the ship's hull are zinc block sacrificial anodes. Nice, hey? There we go. So anything lower than iron on the table, so chromium, zinc, manganese, aluminum, magnesium can be used. You cannot use alkali metals or alkaline earth metals because they just react with water. Yes? So that would be kind of useless. The coating would just bubble away. Right? Do you remember when we put the sodium into water in the fume hood and it went bang? That would be less than useful, right? It would just be like bad. Not all of them are that violent, but they all will react with water. You'll just get bubbles and it will go away. You can watch the Colger video on corrosion prevention. They have good animations. There's a summary there. There's a couple questions there. And that is it. And we are done this book. Woo. Look at us go. Well, technically, there is stuff in the white book, which is the AP extras. Yes. Delta G and K in electrochemical cells. Not much to it. Do you even want to look at it? It just says you can use delta G to find K. Wait. We can use delta G to find K. The equation's right there. We can use delta G to find E and vice versa. And you would have to use Faraday's constant. And you should also know that a volt is a joule per Coulomb. You should know that a Faraday is a Coulomb per mole of electrons. Okay? It's all on the formula sheet. And you remember that thermodynamically favorable is when delta G is negative, when E naught cell is positive, and when KEQ is more than 1 and thermodynamically unfavorable. See, you knew all this anyway. Okay. Huh? This is the white book, I think. Yep. Calculate. Will K be greater than, less than, or equal to 1? Calculate the value of Q. I don't know. Yeah, there's some exercises, not a big deal. Using the Nernst equation, you don't need to be able to use it. But if you're interested, you can take a look at it. Okay, so we're done. Yay. Shall we? We're done chemistry. That's exciting. That's exciting. And we have a whole day before your test.
Thanks.
And we didn't get to do any labs. Would you guys like to do a lab next week?
Oh, we should.
Yes? Yeah.
Are we more doing?
I know, this is the question. What day do you want to come in? Thursday?
Oh, you're on to something.
But isn't there?
No, the open house is at 6.
I don't like it.
Wait, can we do it on Thursday? Because we have a big dissection from 10 to 12.
Yes, we could do it Thursday afternoon.
So from like 12 to like.
After lunch.
And how long would it take?
It's a fairly significant lab, so it would probably take all afternoon. Yes?
Okay, and then I go out next and then I'm at the open. Yeah.
Now, I might on Friday get you guys to make the solution that you need so you don't have to do that step, so you don't have that taking up time. Okay? Yes. Pardon me? I cannot hear the last word he is saying. Yes? For fun? Oh yeah, my marks are due Friday, and I'm going to have you do a lab on Thursday afternoon, and then mark it by the next day. No, it's not. It's for fun. Okay. Questions. We have 20 minutes. Let's do some questions. Yes, Amy. 81. Shh. On just the electrochem review, regular, yeah, okay. $81. The same amount of electricity is used to carry out the electrolysis of palladium, chloride and copper nitrate solutions in separate cells. The masses of palladium and copper were produced and measured and compared. Which of the following is true about the mass of palladium produced? Grams of palladium to grams of copper. So we have the same moles of electrons. Yes. And palladium is 2 plus. And copper is 2 plus. So we will be, if we have the same moles of electrons, we will be producing the same amount of palladium, yes, as copper, the same moles. So how could we tell which one has more mass? We're going to go look at the molar mass. So copper is 63.5. Palladium is 106.42. 63.5, 106.42. 63.5, 106.42. Yes.
Didn't Cu2 plus be Cu plus?
Why? Oh! Because it's copper nitrate. You're right. Good on you for catching that. Okay. So they are not the same numbers of moles. Yes? So they're not the same. We are going to produce twice the moles of copper as we do of palladium. Yes? Okay. So what is twice copper? That is 127 moles. Sorry, grams per mole. Grams per mole. And palladium is 106.42 grams per mole. And so, or actually that would be grams, that would be grams. I'm guessing it's this one because I think that 106 is probably about 84% of 127. 127 equals 84%. Yes. Did that make sense? Excellent. Good, good, good. Next. Yes. 85 and 86. Yes, we can. 85. As the cell operates, where do the electrons flow? So we have zinc and we have tin. So let's go to our data booklet and look up zinc and tin. So here is tin, here is zinc. Yes? So our spontaneous reaction for those two half cells will be the tin 2 plus getting reduced and the zinc getting oxidized. Yes? So the tin is our cathode and the zinc is our anode. So the tin is the cathode and the zinc is the anode, and therefore our electrons move from the zinc. They move towards the tin. And that electrode will, because it is a cathode, it will gain mass. Yeah? Is good? Oh, 85. Did you ask about 85 and 86, not 84? I'm just doing 84 because, like, there I am. Okay. As the cell operates, the electrons flow toward, the cation. Oh my God. Okay. As the cell operates, the electrons flow towards the tin. And as the cell operates, the concentration of tin decreases and the concentration of zinc increases. What happens as a cell operates? Does the voltage get higher or lower or stay the same? It gets lower. I mean, you don't even need to know anything about electrochemistry. You can be like, if a battery is in my remote control, it will eventually run out. Yes? Yeah. So the cell voltage will decrease over time. Well, it's wrong. So it should be B. Okay? Fixed key. Yeah. Okay. An aqueous solution of chromium chloride is, did you want 86 as well? Yeah. An aqueous solution of chromium chloride is electrolyzed using copper electrodes. And we have chromium 2 plus and we have Cl minus. Which of the following would correctly describe the changes in the mass of each electrode as time goes on and the chromium 2 plus in solution? So this is a solution, so we also have water. So we have chromium, water, and chloride and copper. Okay, so we have chromium 2 plus. Chromium 2 plus. We've got water. We've got chloride. And we've got water. So, and we've got copper solid. So we got all kinds of things that could be oxidized, but only one thing that can be reduced, unless I'm missing something. There's no chromium 2 plus going to chromium solid. See it? Nope. So who's going to happen? It's going to be this one. And what did the question ask us? So chromium 2 plus concentration. Chromium is going to turn into chromium 3 plus. So the chromium 2 plus concentration is going to decrease. Oh. There's no option where it says decrease. Well, that's unfortunate. Did you get the same answer as I did, though? You like the same thought process? Okay. Fix question. This question is just screwed up. There's no answer because chromium concentration is chromium 2. Oh, yeah, no. Chromium 2 plus concentration is decreasing because it's turning into chromium 3 plus. So there's no correct answer. No correct answer for number 86. So just cross it out. Okay? Cross out 86. Yes. 75, indeed. Okay, given the following half cell reactions, which of the following best describes the overall reaction in the standard voltage in a lead acid storage battery? Okay. So here's our two reactions. This is a battery, so it's going to be a spontaneous reaction. This one is going to go forward, and this one is going to go backward. So we should rewrite this one going backward and then add up the two together. Yes? Okay, so we're going to write this going backwards. We've got Pb plus SO4. PbSO4, 2 minus, plus 2 electrons. And then we can say we got 2 electrons and 2 electrons. Those cancel out. We have PbO2. We have 4 hydrogens. Oh, that's not, oh, what? The overall reaction. Well, it can't be 1 or 2. Why can't it not be 1 or 2? We want the overall reaction. 1 and 2 have electrons in them, so that's not an overall reaction. But we have PbO2 and we have hydrogen. Oh, look, here's PbO2 and hydrogen. So it's got to be this one. Let's just double check and make sure. We have sulfate and sulfate, so that's 2 sulfates. We have lead, so that's lead. We have PbSO4, and we have another PbSO4. Ah, there we go. And we have 2 waters, so that's the one there. Yeah? Yes? 82? 82. What happens to I minus in the operating cell? Well,
Yes.
omit. It needs a diagram.
82.
What do you mean, what? Do you have any idea how many pages of stuff I churn out every year? Is it any wonder that a lot of it is like wrong?
So we do 19.
19, yes. Plus, for the last 2 years, last 2 times I taught this, we didn't really make it to the end of Electrochem because there was snow. So this review is sort of like been pieced together a little bit. So yeah. All right, number 19. Which one of the following is the weakest reducing agent? We have K is less than 1. Yes? What does that tell us about E naught? E naught is going to be negative. Yes? So that means that is this reaction wanting to go forward or backwards more? Backwards. And if it's wanting to go backwards, that means that our stronger things are over here, just like in acids and bases, yes? And our weaker things are over here. And so then we just have to decide who is the reducing agent. It's the thing getting oxidized. So W is getting oxidized in the forward process, yes? So it is we have reducing agent, oxidizing agent, reducing agent, oxidizing agent. These guys are stronger because they're pushing the reaction away. These guys are weaker. So W is the weakest reducing agent. Yes. 27, yes. Did this work okay for you guys? 19 is good? Yeah? Cool. 27, was it? Yeah. Okay, 27. Which of the following could be the product of a reaction where NO2 acts as an oxidizing agent? If NO2 acts as an oxidizing agent, it gets reduced. Okay, and if it gets reduced, then am I putting more oxygens on or am I taking oxygens off? I'm taking oxygens off. Yes? Now, you can go through it by doing the oxidation number. You can say, okay, I've got -4, so N is +4. And then down here, you can say this is -2, so that's +2, so it got reduced. Yes? Yes? Yeah? 93? What reaction occurs at the cathode? So we have copper 2+, I-, and water. At the cathode, we have reduction. I- cannot get reduced, right? Because it would become I2-, which is just impossible. So we just have to compare copper and water. So we're really looking at these two. It can't be this one because that's oxidation, right? These are both oxidation. So let's go look at, oh, I think it's this one. Because isn't copper 2+ above water on the chart? Like, I feel like we've looked at that one a lot. is copper 2. Oh, yes, here's copper 2 plus getting reduced. Here's water getting reduced, so copper 2 plus is preferentially reduced. Well, the answer key is wrong. Sorry, what? Let's go back here. Let's make sure I say to fix that. It should be B. Fix key. All right, who's next? What's next? Yes. 66. A student wants to determine the concentration of tin in a solution of tin 2 chloride by a redox titration, a suitable ion. So you need something that's going to react spontaneously with tin 2 plus. So go on your chart and figure out which one of those things will react spontaneously with tin 2 plus. And tin appears in the oxidizing agents and the reducing agents. So you can look both places. Okay. So tin 2 plus. There's not a lot of them. I think it's iron, copper, and tin. I'll do that. Here's tin 2 plus. Here's tin 2 plus. And we have bromide, Cr3 plus, lead 2 plus, permanganate. Br minus. Br minus, chromium 3 plus. Chromium 3 plus. MnO4. MnO4. There we go. Oh. Yes. Ding, ding, ding. Got it. Plus, if you remember what I said about redox titration, it's usually permanganate. Because it self-indicates and it's really high up usually. This one isn't acidified, but even that there's still a reaction there. Yay! Hiya. Yes, let me grab that for you. There you go. You can just send it anywhere there's space. Yeah. Yes. I'll come to you. I'll come to you. You don't have to gather everything. Number 4. Okay, so you've got silver. Okay, so we have silver. That looks good. Yeah. 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 So yeah. Oh, so the answer is no. So the answer is no because the reaction will occur, but that is not part of the reaction.
So, it has silver in it. In the copper.
Well, silver. Okay, so copper is smart use to oxidize on silver. So no. Yeah. Yeah. And then you've got lead. What? Yeah, because this is yes.
Like,
Oxidation versus piano is not necessarily in a galvanic cell, they're going to use cells, it could be something else that is being oxidized. Something is going to get oxidized again, whether it is the anode itself or Okay. What's the oxidation potential of water? What is the oxidation potential of solid? Yeah. Let me go grab that. Okay, we got these here. So, about
I can hear it.
There you go.
Thank you.
So, okay, so the pages we're gonna be doing, I think, I always change my mind halfway through the lesson. And it's possible I could do that. Like, I'll feel bad about it, but I could do it. I'm pretty sure that today we are going to do. Oh, you're here today? Okay. So today we are going to do 5.3. Okay. And should I have looked at all of them? You know what? I don't think we're gonna get to chromosomes. Okay. I'm so sad that we're not getting to chromosomes, which is why I might change my mind partway through.
And if you do, just like email me or something. I'll stay on my email.
Okay. And then I don't know if I want to do the RNA because it's a little bit in depth, but maybe it's.
So funny story. I've been able to go on and teach people all about RNA. And I was like,
okay. So yeah, you know what? We're gonna do this ones because then at least, we can be like, and maybe we'll get to here by tomorrow.
okay, so I'll focus on these three.
Focus on those three for now, and I think we'll get through this as well. And then probably not chromosomes, which saddens me, but there we are.
And if you do,
yeah, I'll just email you. Yeah. Good stuff. I love your braids because all the colors in your hair.
yeah, I actually, so this part is bleached because I dyed my hair
Okay,
pink
yeah.
last year. So there's nothing in there.
That's very cool.
Yeah, it was for
But are
softball.
the other highlights yours, your own?
Some of them are mine.
Okay.
I can't tell which one's bleach
Yeah.
and which one's not.
Yeah.
Because my mom does my hair.
Oh, very nice.
She's got all blue up top. She loves to dye.
Oh,
her
that's
hair.
amazing.
Yeah.
Yeah.
Like she goes through her main 3 colors: blue,
Yeah.
purple, and green.
That's so fun.
Right?
That's
yeah,
so much fun. Yeah.
She always dyes mine.
All right. See you later. I did mark the quiz. Yeah. Where did I put them? It should be right here. There you are, right there. Okay. Oh, thank you. Yeah, I know. It's kind of trying to die because the inside like part is not as waterproof as it once was, but I keep using it because I love it. Yes, Hudson is writing the quiz right now, so just don't like have it out beside him. But yes. Here we go. Oh, I haven't recorded the enriched yet.
Oh.
So let me grab that and record that.
Do you think I could take a look at mine, please?
Yes, absolutely. Just let me record the enriched here. You just have the best outfits. I swear to God. Doesn't she?
I'm in socials. I'm like, you're just walking them like fake things. Actually.
Thank you. Are you here to get your quiz or something else? I do. So I'm looking for Vivian and Emily and Barini. Okay, Vivian.
Where'd you get your I like this one.
Nice.
Wait, is it you 66 or 60?
66.
Oh.
And Vivian.
I didn't finish yet.
Pardon me?
I didn't finish mine.
Oh, that would explain it. I was like, hang on. Why don't I not have yours? There you go. No, it'll be at least proficient. Yeah.
Okay.
90%. Proficient. There you go. A nice strong proficient.
Okay, thanks. I've been like running around because I have PE and I've been like playing badminton for 1 hour. And then I went to my library, that's closed, and I went to my English class. They're having a parent teacher meeting. And if this class is not open, I don't know what I do. Thank you for keeping the class open. I was preparing for chemistry and physics enriched. And, is it the enriched that the booklet that you gave, or is it also that are marked in the box?
I have no recollection.
Do you? Okay, I can show you the box.
Yeah. Yeah. Now, what is it that you want from me around these? Because I don't really know.
Oh, I just want to bring my grades up in case I have them down because I joined late.
Okay.
Okay.
Yeah.
I tried to open like my ad, but it keeps on like disabling my account. You try to log it in.
Yeah. Have you tried it on a computer?
No.
You want to try it on a
Probably on
computer?
laptop or like this.
Yeah. Here, I'm just gonna press